Hey folks, so in this point in the semester I want to introduce one of the last linear algebra components that we're going to be dealing with, and that is that of an eigenvector. So we're going to introduce the notion of an eigenvector to a linear transformation or its associated n by n matrix. So in this section we will just be studying the eigenvalues and eigenvectors, and we will then see how those apply to solving systems of differential equations in a later section. So let's go ahead and get started. What is an eigenvector? Well, let's let T be a linear transformation from Rn to Rn. Then we've shown that T has an associated matrix A. So by an eigenvector, we mean an eigenvector of A is a vector V so that AV, when I multiply A to what I'm claiming its eigenvector is, or an eigenvector of it is, I get the same thing as if I simply multiplied V by some scalar. So let's just check, see how the dimensions on this work. A is an n by n matrix, V is an n by 1 vector, and we're saying that that's equivalent to multiplying this scalar times an n by 1 vector. So the net effect of the transformation, so one way to think about this is we're doing a transformation to all the vectors in Rn. When we do the transformation to what we're going to call an eigenvector, it simply gets scaled rather than shifted elsewhere in the Rn plane. So the transformation doesn't have any effect on an eigenvector other than to scale it by some factor lambda. Okay, so this is for lambda, just a real number. So keep in mind, we've got here we've got a matrix times a vector, and that's equal to a scalar times that same vector. And if we can find such a scalar, then we will call V an eigenvector, and we call lambda an eigenvalue. So we've got these two paired notions, that of an eigenvalue and that of an eigenvector. And we'll also introduce the notion of an eigenspace here in just a second. So sometimes I'll just refer to all of these different components, values, vectors, and spaces, as Eigenstuff, because they all go hand in hand with one another. Okay, so we'll look in more detail, and when you watch the 3 blue, 1 brown video, you'll see a little bit more about what we mean by an eigenvalue and eigenvector. We'll learn how to compute those, and then we'll actually see why they're useful in subsequent videos. The last thing I want to go into is what is the eigenspace of an eigenvalue. So let's let lambda be an eigenvalue associated. So we can associate an eigenvalue or an eigenvector either with the transformation or with its associated matrix. So let's say associated with a linear transformation. Then the eigenspace of lambda, and we're going to denote that this way, the eigenspace of lambda, so we'll use E in that bold notation that we use for vector spaces, of lambda is the set of all vectors V such that AV is equal to lambda V. So if you're looking at the definition of an eigenvector, what an eigenspace is, it's all the eigenvectors that have the same eigenvalue. So i.e. all eigenvectors of T, I guess we didn't name this linear transformation here, with the same eigenvalue. Okay. Folks, these are challenging definitions. We're going to see a little bit more about them as we go through this sequence of videos, so stay tuned.